we proceed, let's look at quickly what we did in lecture number 12. So in lecture number 12, we essentially reviewed the very basics of quantum mechanics. We looked at what a state vector is, which is just a mathematically an abstract quantity. Then we looked at the wave function, which is the projection of the state vector onto a given basis. That gives us the wave function. We looked at the probability density, which is the absolute square of this projection, that is the wave function, that gives us the probability density. If it's a discrete basis, this actually is the probability itself. Then we have operators within quantum mechanics, which is what we operate these state vectors with in order to get some the value of some dynamical variable. Or we also have unitary operators that evolve the state. This is just one example of a momentum operator in the position basis. This is the position basis representation of momentum operator. We also looked at the concept of eigenstate, which is that if the system is in an eigenstate of some operator, then if we act that operator on that particular state, this state remains unchanged and we obtain the eigenvalue. So this one is the example of a momentum eigengate, and this is the position basis representation of that momentum eigengate. We also looked at the change of basis. That means one basis vector, a basis vector in one basis can be represented in terms of the basis vector some other basis. Here we are representing a position basis vector in terms of the momentum basis vectors. So this is how we can go from one basis to the other. This we can also use for calculating the wave function in one basis, knowing the wave function in some other basis. We looked at the concept of measurement in quantum mechanics in brief. We will look at this in some more detail in some other lecture. We then looked at the expectation value, because the main point in the measurement is that the measurement outcome within quantum mechanics cannot be predicted even in principle, and that's why one needs all that one can calculate is the expectation value, which is the expected value or the average value that one obtains of a physical variable if the measurement is carried out infinite number of times. The expectation value of an operator is given by this formula, where the psi is the state and x operator. Then we have uncertainty in quantum mechanics, and that is defined in terms of the expectation value of the first moment x and the expectation value of the second moment. We also looked at the Heisenberg uncertainty principle, which basically says that if you have two conjugate variables, then they cannot be measured with infinite accuracy at the same time. So if we know the position very accurately, we cannot have very accurate information about momentum, to the extent that the product of the uncertainties has to follow this inequality, which says delta x delta p is greater than equal to h bar by 2. We have similar uncertainty relation whenever there is any pair of conjugate variables. So we have similar uncertainty relation for time and energy, as well as angle and orbital angular momentum. We then looked at how to handle fields within quantum mechanics. So for massive particle, we have this is how we represent Hamiltonian, and for massive particle we work with position momentum operator. But in handling fields, we write the Hamiltonian in terms of the electric and magnetic field operators, and then they are within the quantization, they are represented in terms of this creation and annihilation operator. Again, the electric field operators can be represented in terms of these creation and annihilation operators like this. When we handle the fields, then we represent the state of the field in the numbered state basis. For example, this n of omega, this is the state with n photons, state of the field with n photons, each with energy h bar omega. The way the creation and annihilation operator work is that if you have an annihilation operator operating on a state with n photon, then it yields a state with n minus 1 photon. If it operates on a vacuum state, it gives a 0. If a creation operator acts on a vacuum state, that means state with 0 photon, it generates a 1 photon state. And if it acts on a creation operator acts on an n photon state, it generates a state with n plus 1 photon. Okay. So now we want to get into the quantum description of coherence, but before we do that, I just want to establish a few connections between classical wave mechanics and quantum description of fields as far as interference and coherence is concerned. So in the classical wave mechanics, when there is no randomness, we write the state in this manner. For example, here this is the time domain signal, and we are writing this as a frequency domain signal in this form, just like as a Fourier transform. We can have a space domain signal, and that we can also write as a spatial in terms of spatial frequency domain signal. Similarly, a signal in the angle basis can be written in terms of the signal in the orbital angular momentum basis. So this is the state description when there is no randomness within classical mechanics. So again, even in quantum mechanics, we do things very similarly. When there is no randomness, the state is referred to as the pure state, and in that case the state can be represented as a superposition. So for example, here the state is represented as a superposition of several frequency states. Similarly, a state can be represented as a superposition of several q, the spatial frequency states, and here we are representing it as a sum of several orbital angular momentum state. Now if we take this state and if we take its projection on the position basis, that means I am taking the projection here as x, so that is the only kit. So then again the projection over x. So this equivalent can be written like this, which is say psi x is equal to aqx, iqxx, dqx. This is just the wave function. This is a state representation. This is the wave function representation, and we can see that this representation and this representation, they are very similar. Similarly, for the discrete basis, we can again take the projection, and then this is the wave function in the phi basis, and then we see this representation again is very similar to that representation. So when there is no randomness, the state in quantum mechanics is referred to as a pure state. Now when there is a randomness, we know that even within classical wave mechanics, this way of representing the field or the signal, this just becomes symbolic. The real meaning is only given to the correlation function. So even though we have seen, even though when we represent the function like this, if this v is random, then this we treat only as a symbolic representation, and any meaning is only given to the correlation function, and the correlation function is defined as v star phi 1, v phi 2. So this is the correlation function, and I mean this quantifies the correlation in the field at points phi 1 and phi 2. So this is just an example we have taken for the angle basis. And if we write in terms of alpha L's, this is how it's written here. Since the alpha L's are the random quantities, so we take this ensemble average over here. Similarly, if the process is random, then we refer to it as the mixed state in quantum mechanics. So in quantum mechanics, there are two kinds of randomness. One is the intrinsic quantum is the intrinsic randomness because the quantum system, and other one is this randomness, which is pretty much what we see in the classical. So we can say this is like the classical kind of randomness or the mixture, and that's why the name mixed state. So when we do have this randomness, we refer to the state in quantum mechanics as a mixed state. So for a mixed state, that means when there is randomness, this extra randomness beyond what's there in quantum mechanics, we write it as rho, and this rho is defined as the outer product of this psi, and then we take this outer product and then we take this ensemble average. We can see that this description is very analogous. Here we have v star phi 1, v phi 2, here we have ket psi, bra psi, and then the ensemble average. So if we just use this notation, we can write this rho like this. And so the only ensemble average we need to take over is this quantity. Now if you take the matrix element of this rho over phi 1 phi 2, then this is essentially this quantity, and if we calculate this, we get this. So this is the matrix element, the density matrix element is basically the same as the correlation function over here. So the density matrix element within quantum mechanics play the same role, very similar role as do the correlation functions in classical description. So here I just wanted to kind of establish a parallel between the classical and the quantum way of describing fields and interference. Okay, so now that we know that the correlation function in classical wave mechanics and the matrix element, the density matrix element in quantum mechanics, they play a very similar role. Let's just look at one special case, that when the eigenmodes are correlated, at least in this example, then we know that this alpha L1, alpha L2 star ensemble average, this just becomes a delta function. So this is SL1 delta L1 L2. That means this quantity is 0 if L1 is not equal to L2, and this quantity is equal to SL1 when L1 is equal to L2. So in this case, we know that W phi 1 phi 2 is written as a single sum, and in this case the rho that we have over here can be written like this, the SL L outer product. So this is diagonal mixed state. So here we have the density matrix, and the density matrix, if you have this kind of correlation, the density matrix has only diagonal elements. The other concept of OM spectrum and OM spectrum getting related to this W, they remain the same even within quantum mechanics. So again, the density matrix element and the correlation function in classical mechanics, they play very similar roles. Okay, so an example of a pure state. So let's take a laser. Suppose laser gives us the horizontally polarized light. Now let's divide this light using a beam splitter. So half of the light goes here, half of the light goes here. Of course, this is horizontal. The light goes there is also horizontal. Now let's introduce a halfway plate. So then that will convert this horizontally polarized light to the vertically polarized light. So now we mix these two lights on a beam splitter. So we have horizontally polarized light coming from this side, vertically polarized light coming from this side. So what is the state of the light that is over here? So that psi is equal to the superposition of H and V. Of course, we'll have alpha and beta, which will depend on the splitting ratio and other factors. So in general, psi is a superposition of alpha of horizontally polarized light and vertically polarized light with coefficients alpha and beta. And this is a coherent superposition. This is a coherent superposition of H and V. And when alpha and beta, they are both equal to 1 over 2, then this psi is essentially 1 over 2 H plus V, then this is just a 45-degree polarized light. So when we add this horizontal and vertical polarizations, what we obtain is a 45-degree polarized light, and this is also a pure state. So this is an example of a pure state. A coherent superposition basically yields a pure state, or a basis vector itself, that is also a pure state. Now what is a mixed state? Now the example of a mixed state is the following. Let's take two separate lasers which are not connected in any way. So these are two independent lasers. Now if this laser gives horizontally polarized light and this laser gives a vertically polarized light, and if we combine them on a beam splitter, what is the state we are going to get? This state won't be a coherent superposition of H and V, because there is no phase relation between the field or the state coming from this source and the state coming from this source. Here in this example, the state coming from this source and the state coming from this source, their phase correlate because they are coming from the same source. But here, since the two sources are very different, independent of each other, the state coming from this source and the state coming from this source, they have no phase correlation between them. So they are completely random with respect to each other, and hence the state psi is not a coherent superposition of the states coming from the laser 1 and coming from laser 2. So what is the state then? So state in this case can be represented by density matrix. The state is no longer pure. The state is represented by density matrix, and then we write the state as HH, the outer product, and VV, outer product, and alpha square is the proportion of the H and beta square is the proportion of V. That is the state we have. And this is known as the incoherent superposition of state. This was the coherent superposition, this is the incoherent superposition. Here alpha is a complex number, beta is a complex number, there is a fixed phase relationship between them. On the other hand, in incoherent superposition, the alpha squared, that's a real number, not a complex one. Beta squared is also a real number, and of course there is no phase relationship between. So that's why it's called an incoherent superposition, and this is what gives the density matrix. And of course, when alpha and beta are equal to 1 over 2, same as over here, then we get rho as half HH plus half VV, and this is just an unpolarized light. So if we add coherent superposition, if we add horizontally polarized light and vertically polarized light in a coherent manner, what we obtain is a 45-degree polarized light. But if we add the same light in an incoherent manner, what we obtain is an unpolarized light. And this is precisely the difference between a pure state and a mixed state. Pure state is a coherent superposition, mixed state involves incoherent superpositions. In fact, the example we did for the coherent mode representation in the polarization basis, we saw that that a general polarization state can be written like this, and this is a general partially polarized state. So this is actually a mixed state in the quantum language. This one can always find a basis x prime y prime in which this state can be written as in this form, which is a diagonal form, and then this we saw that can be written like this. That means a general mixed state can be written as a sum or incoherent sum of two pure states. This is the pure state that is polarized along x prime. That's another pure state polarized along y prime, and this is a incoherent superposition of the two states. So in general, a mixed state is given in this form, and if we do a basis transformation, then a mixed state can be written as a sum of those basis pure states. Okay. So now that we know the pure state and mixed state, we want to look at how to calculate the expectation value of an operator, when it's a pure state versus when it's a mixed state. So for pure state, we have seen it already in the last lecture when we calculated the expectation value of the position operator. I mean, same calculation will go for any other operator as well. So for the expectation value when the state is pure is given by this kind of formula. So the expectation value of x is just psi x psi. And so I mean, if it's any other operator A, the expectation value just has a similar expression, that is operator A is psi A psi. So this is when the state is pure and we can write it as psi. But what about when the state is mixed? So when the state is mixed, we write it as psi, that outer product, and the expectation value of this quantity. Now again, one can always find a basis. This is represented as psi, but one can always find a basis. Let's say the basis states are psi I. So one can always find a basis in which this can be represented as a single sum. So here we are writing a single sum as pi psi I psi I. So this is basically, these psi i's are the pure state, and we are writing this mixed state density matrix as a sum of incoherent sum of those pure state, and pi, these are the weightage of those different pure states. So this psi I, this is again density matrix corresponding to that pure state that we can write as rho I. So this rho we can write as a weighted sum over this rho I, and where pi is the weightage. So if this is the mixed state, then what is the expectation value? Now the expectation value of an operator, I mean, if it's just a pure state, then this is the expression. But if it's a mixed state, then this expectation, for calculating the expectation value, we actually have to calculate the average value of this expectation value over all the different states that we have over here. So that means this psi I, A psi I, that is the expectation value when we just have the pure state psi I around. But now we know that our mixed state is represented as a weighted sum over several pure state. That's why the expectation value now is also a weighted sum of the expectation values over all these different pure states. So and this pi is the same weightage as it is over here. So this is the expectation value of the mixed state. And if we then I mean, we can just add here is this psi j and psi j sum over j. This we are putting in here because this quantity is just equal to 1. That is because of the completeness of the basis. So the psi j that is equal to 1. We can write it like this. Then we can just interchange this because this is a complex number, that's a complex number, so we can write it in this manner. And now we can take the psi j, just outside the summation, put this the I summation over here, and we can write it like this. And now we realize that this psi I, which again is a sum over I, which again is just 1, because of the completeness, using that we can write this as psi j rho a psi j. Now the psi j rho a psi j is just a trace, I mean we have this rho times this a, and the psi j which is simply the trace. So this quantity is basically trace of rho times a. So rho is a density matrix, and we also know a has to be a density matrix when we write it in that basis. And so the expectation value of an operator for a mixed state is given by this formula, that a is trace rho a. So here we have taken this discrete summation, but it could be that the density matrix rho has a integral over here. It is not a discrete summation, but it's just the sum of, or the integral of, infinite number of terms, in which case this will go as integral, but the trace will still remain. So this is the expectation value when the state is pure, this is the expectation value when the state is mixed. Just to now conclude this pure versus mixed state discussion, when we have pure state, the dynamical equation we have, that's the Schrodinger equation, H psi equal to I h bar del psi del t. But when we have mixed state, we use the commutation of H rho, that is equal to I h bar del rho del t. We won't be using much of this, but that's the connection equation one uses when one has the mixed state. Here again, I just want to kind of re-emphasize that when we calculate, even for pure state, we calculate expectation value, and this is because in quantum mechanics the outcomes cannot be predicted because there is an inherent uncertainty. So even for a pure state, there is an inherent randomness because of which the exact outcomes cannot be predicted. This feature is not there in classical mechanics, and that's why we talk about the expectation value even for pure state. And when we talk about mixed state, this is an extra layer of randomness that comes into the system, and this randomness has an analog in classical mechanics. We have similar randomness there, and then the expectation value is now calculated by this quantity, which is basically a double expectation value over here. Okay, so as we saw the field quantization, that within quantum mechanics, when dealing with particles, we work with position momentum operators. When dealing with fields, we don't work with x and p operators, we rather work with the field operators, electric and magnetic field operators, and the position and momentum, they simply act as parameters. All the dynamical variables, that means all the operators corresponding to the dynamical variables are expressed in terms of electric and magnetic field operators when working with fields. And we saw that the state of the field is represented in terms of the number of quanta of energy. So within field quantization, the electric field is represented like this. So this electric field as a function of R and T. We can write it as in the frequency basis as the E r of omega to the I minus I omega to d omega. So this is writing the electric field operator in terms of the frequency domain operator. And since for representing any physical system, we will be interested only in the electric fields that are real, we'll have this relation that E dagger r omega is equal to E r minus omega. We had derived very similar relation when we were working the complex analytic signal representation within the classical coherence theory. So this is very similar, there is no difference here. Now this electric field, when we are writing in the frequency domain, we have this integral from minus infinity to infinity. Now this we can write as minus infinity to 0 and 0 to infinity. Same here. Now if we then do a substitution of omega to minus omega, then we can write it in this manner, just replacing omega with minus omega, and we know that now this quantity is the E dagger because E is real, and so we can write it like this. So an electric field operator, we can write it in this manner in the frequency domain, and this we see has all the positive frequency part, and this one is the negative frequency part. So we write this one as E plus and this one as E minus. So that's this is the electric field operator, this is the total electric field operator, this is the electric field operator corresponding to the positive frequency, electric field operator corresponding to the negative frequency part. And the positive and negative frequency parts are mutually adjoint. That means E minus RT is equal to E plus dagger RT, and let me mention here that the positive frequency part of the field operator, this E plus RT, plays the same role as the analytic signal BRT. Okay, so now that we know that the positive frequency part of the electric field plays the same role as this analytic signal in the classical coherence theory, we then want to kind of find parallels between the different concepts we have in classical that we want to see in quantum. So in the classical, first concept we encountered when dealing with the coherence theory is the concept of intensity, and the classical intensity is defined as V star RT V RT and ensemble average. Now in quantum mechanics, we don't have the concept of intensity. One rather asks the following question as to what is the probability that a photon is absorbed at RT. One doesn't ask what is the intensity, but what one asks in quantum mechanics is what is the probability that a photon is absorbed at RT. This is an equivalent question in quantum mechanics. Now the way this is obtained is that we assume that the state of the field is I. That's the initial state, and after the photon has been absorbed, the field goes to the state F. So this is the state of the field I. After a photon absorption, the field goes to a state F. This could be a manifold of states as well, need not be just a single state. So what is the probability that field absorbs a photon and goes into the state? This can be calculated by this transition matrix element, that this is the initial state, this is the E plus annihilation operator, and this corresponds to the absorption of a photon, because of which the field goes into the state F. So this transition matrix element, this represents the probability that a field absorbs a photon and goes to this state. This represents a probability that a photon is absorbed at RT. If we just expand it, we can write it like this. This is a dagger and this quantity. If we now evaluate this quantity, we kind of swap this I and F, and then this E plus becomes E minus. So these are two equivalent representation. And since we have this F here summed over F, this basically is equal to 1, because this manifold has to make a complete set. So this quantity essentially becomes this. So what we have here is that this probability that a photon is absorbed at, let's say, RT is the expectation value of this quantity, E minus RT, E plus RT. So this is the expectation value of this quantity taken over the initial state I. So this is the photon absorption probability. Now, if the state is not pure, then this probability PRT, in order to calculate it, we'll have to take one more expectation value, or ensemble average, and that gives the probability. And we know that this is basically the trace of rho times E minus E plus. So this remains the same. This mathematical structure remains the same when we calculate the probability for the mixed state. So if it's a pure state, this is the probability, which is the expectation of E minus E plus. When it's a mixed state, then we have to take the trace of rho times E minus E plus, where rho has this representation. Now the next concept we have in classical description after intensity is the correlation, because this correlation function, this describes how the field points are, how the field vibrations at 2 points R1 T1 and R2 T2 are correlated. Now, how do we get a similar quantity in quantum mechanics? So the way to define it is like this. So we have E minus E plus over this initial state I, and of course, since we are talking with the correlation function, of course we are not talking pure, so we are talking the mixed state, and so taking the ensemble average, or in other words, the trace of rho E minus E plus. So that is how we define the correlation in quantum mechanics. Again, let me mention here that although we are establishing the equivalent of intensity in quantum mechanics, but we know that the classical description, as we saw in the very first lecture, the classical description is actually inadequate when it comes to experiments with very few photon. But the quantum description, where we calculate things in terms of single photon, is actually absolutely correct at every light level. Okay, so coming back here, this correlation function, this G1 that we defined in quantum mechanics, this plays the same role in quantum description as does this correlation function in classical description. Okay, so now how do we define interference within quantum description? So the interference within quantum description is defined as or described as a single photon interfering with itself. So this is a very famous statement by Dirac, where he says that single photon interferes with itself. So let's just look at this one photon interference. This we had already done in our classical description, but we'll now try to do it using quantum description. So here is the Michelson interferometer. Photon starts from the source and gets to the detector. It can get to the detector in two different ways. One is that the photon starts like this, goes to the upper mirror, and then comes to the detector, and that I am representing like this. The photon starts from here, goes to the mirror, and comes back, and that we are representing like that. And so this can, one way of writing this is just we can write this in terms of this unfolded diagrams, and then the interference happens. We say that the interference happens between when this alternative pathway interferes with this alternative pathway, and in that sense Dirac kind of says that a single photon interferes with itself. So that is the intuition behind it. I mean, a photon can either go this way to the detector or this way to the detector. Of course, it cannot be in both the possibilities or pathways, but the way we explain interference is that this possibility and this possibility, these two actually interfere in the quantum description. And as far as doing the math, then we calculate the E plus operator at the detector. This we can represent in terms of the electric field operators at time t minus t1 and at time t minus t2, because what comes through this one takes the field at t minus t1, and what comes to this one has the field at t minus t2. Again, this is very similar to what we do in what we did for the classical interference. And so once we have this, then in this case we are not calculating the intensity, we are calculating what is the probability that one absorbs one photon or detects one photon at this detector, which is just this quantity as we saw, and then this can be expanded like this. So again, we have the first term which represents the photon absorption probability for the photon coming through first alternative. This is from the second alternative, and this is from the cross term. So in this sense, the structure is very similar to what we see in the classical interference. There's no difference, but the interpretation is quite different. In the classical, we measure the intensity and we say part of the field coming through this and part of the field coming through this, they basically interfere. However, in quantum, we say the photon either goes through this path or it goes through that path. Single photon cannot simultaneously be in both the paths, and this possibility of the photon going this way and that way, that basically interferes. And we know again that the classical description works only at high light level, not at low light level, but this kind of description works at every light level. So math wise, it is very analogous, very similar, but the interpretation wise, things are quite different. Okay, so when we are doing fields, we can actually also ask this next level question, that what is the joint probability that one photon is absorbed at R1 T1 and another photon is absorbed at R2 T2. So we are not asking just one photon, but we are asking about two photons being absorbed. So for a pure state, we will just again calculate the transition matrix element that a photon is absorbed at R1 T1 and another is absorbed at R2 T2. And if we do a very similar calculation, what we find is that this probability is basically given by the expectation value of this quantity, which is E minus R1 T1, E minus R2 T2, E plus R1 T1, E plus R2 T2. And this is also known as the coincidence probability. And of course, if the state is not pure, then we have to take one more level of expectation value. And in this case, it is just a trace of rho times this quantity. So it's the same mathematical structure. So that is the joint probability that one photon is absorbed at R1 T1, another photon is absorbed at R2 T2. So now when we have these two photons being detected at two separate points, one can talk of now 4-point correlation function. So when we had just one photon, then we were talking about 2-point correlation function. With two photons, we can talk about 4-point correlation function. And this correlation function we can write as this G2, which is the expectation value of this quantity, which is E minus R1 T1, E minus R2 T2, E plus R3 T3, E plus R4 T4. So the R1 T1, R2 T2, R3 T3, R4 T4, these are the four different points. And so if it's a mixed state, then of course we have we write it as a trace over this quantity. Okay, so this quantity we will use when we are dealing with two photon interference. That means here we're detecting two photons, so this quantity we'll be using when we deal with two photon interference, because there we will require as to how the field vibrations are correlated at these four separate points. And this 2-point correlation function that we just discussed in the last slide, that we will use when we discuss the one photon interference. Okay, so I will stop here. Thank you.